Okay, when do you want your midterm exam? Before the spring break or after? Before you decide the pros and cons, so if you have earlier midterms and before March 4th, so 4th to 11th is spring break. So before March 4th if you have, then it's early, you get less time to study, There's the con. The pro is you have less material to study. Now if you take after midterm, you have long time to study, you can enjoy your, you have a spring break, after spring break if you get midterm. Then you can, the pro for having midterm before spring break is you can enjoy your spring break. So if you have it after, then you have more time to study. That's the pro, that's the only pro. The other problem, there are two problems, is that you cannot enjoy spring break and you have a lot of things to study. So which one do you want? If before, then we will have to have it on February 28th. What happened? You have one more paper on that day. So then we have to do it after. Because until 28th we won't cover much to have it. That I know you would like, but that's not what I like. So let's, somebody had travel plans after spring break, yes? When are you returning? So you are returning February, you don't count it. Now after spring break, somebody had plans? Yes? When are you returning? Next week? Okay, I'll let you know. I have to schedule something. So it will be either on the 14th. In that case, if you are not here, you can come to the office hours and take it. Or it will be on the 19th. So I'll have to select in one date between the two. Okay. So either on the 14th or 19th, if you cannot make any of those days, just come to the office hours to take breakfast. Okay. You are leaving some? On that day? Then I cannot do there's too many variables. Yeah, so if you cannot take it, you just come to the office hours. But don't, everybody shouldn't come to the office hours. You have to have legitimate reason. The assignment will be posted tonight, and we hope to start the data collection by Wednesday. So you have, by this time I think you have found your groups. If not, form it. And I will post the list of science you need to know. You just don't have to learn, you just look at those ones. Once you come here, you can learn also. Yes. You had a question? Oh, yeah, again you are calling your friend. 5%, yes, group is 5% per group. Right? Make it a point. You have 5 people. Now, I didn't expect that there will be 195 students. Otherwise, I would have allowed 4 and I would have planned better. But 5% means there are 40 groups. Data collection takes 1 hour, 40 hours. We have to work 40 hours to collect data. You have to work only 1 hour. That's not fair. So you have 5 people. Anything else? So let's get, you had a question? It's very difficult to understand who has questions. So let's start. Let's start with our discussion again. Let's continue actually. So we are talking about principal component analysis, and we said that you take the covariance vector and covariance matrix of the data, and you find out the eigenvalues and eigenvectors. So we need some background on matrix multiplication and all the matrix operations. So I hope you have read up on that. We get the eigenvalues and eigenvectors, and we saw that those are two very important characteristics of the matrix. because using eigenvectors and eigenvalues you can represent a lot of things. You can represent a lot of things of a matrix. So now, so we said that okay, you take the covariance matrix and the direction, because eigenvectors are directions, right? The direction which has the maximum eigenvalue, then that means in that direction the entire data has the maximum variance. Right? So now that direction becomes a representative projection of the data. That is what PCA says. Now what you do with low eigenvalue directions, PCA doesn't care. You can delete them, you can not delete them, doesn't matter to PCA. PCA only says that okay, these are high variation directions. So basically what PCA does, the output of the PCA, is that it says that okay, don't look at XY axis, look at some rotated axis. That's what PCA tells you. Look at some rotated axis. So which means that the eigenvectors are the new directions. So if they are the new directions, what does it mean? What does it mean to the for the data? You as a data analyst, what do you make out of eigenvectors of covariance matrix? So it is almost like this. I need to use. So you have gotten some eigenvectors. So eigenvectors means it's a new direction. Let's say this is an eigenvector E. So this E has what? C1, C2, if it's a two dimension. Right? It's like a vector. So what does it mean? If you have a data matrix A, so A has some values, right? If you have some data matrix A and you are multiplying with E, what does it mean? What is the resultant? What?
Eigenvalue.
That's what I. What?
Eigenvalue in eigenvalue.
E is not an eigenvector of A. E is the eigenvector of covariance of A. Covariance matrix of A. So if you multiply E with A, you don't get eigenvalue multiplied by A. Right? You get, if you multiply E with covariance matrix of A, then you get, but not this. So what does that mean? A multiplied by E, what do you do? So if A is a 2 plus 2, let's say not 2 plus 3, let's say A is a 2 plus 2, so delete this. So if A is A, B, C, D, right? And eigenvector you have gotten is W1, W2. So if you multiply, what happens? A, W1 plus B, W2. That's the first one that you get. Right? You get a vector like this, AW1 plus BW2 and CW1 plus DW2. You get this, right? So what is it saying? Instead of 2 dimensions, you can have 1 dimension, but you combine the 2 dimensions using this weighted average, W1, W2. Right? So W1, W2 are the weights using which you can combine the dimensions. So this gives you new feature dimensions. These are new feature dimensions. Right? Which means this is not just x and y, this is some combination of x and y. That is what PC is giving you. So when you get the eigenvectors of the covariance matrix of A and you multiply it with the data matrix A, not the covariance matrix of A. When you multiply with the data matrix A, you get new dimensions. So whenever you do PCA on a data, you will have to argue about why did I get these values for eigenvectors? Because these values means that they are saying that the topmost, the highest eigenvalue vector means that is how you should combine all the axes and you have the highest variance. So now these weights represent which dimension is more important. Whoever has this weight, higher weight, that dimension is more important. Right? So that's how you make sense of PCA data. So we'll use this in assignment 2. Right? I don't know, maybe 3, assignment 3. Yeah. Assignment 1 and 2 are very simple. Data collection, that's assignment 1, and annotation is assignment 2. The 3 is where we will get more and more complex. So we'll talk about that in assignment 3. So now let's go back to the presentations. We'll breeze past these presentations because these are some topics that are background knowledge basically. We haven't yet gone to the actual stuff. So this we don't need to understand. This is it says where PCA falls in the whole scheme of things. Some examples. No need. Okay, so that is one way of dimensionality reduction. Another way is feature subset selection. Right? So you go, you extract some features from your data. You don't use the whole feature set. Right? There are certain redundant features, there are certain irrelevant features. Redundant features mean features that are repeated. And irrelevant features means features which don't give you much data, much information. So that is handcrafted features. So which means you know the features and you decide which one to keep. You don't use a mathematical model. It's just through intuition. Now there are many different techniques. So you brute force approach is one. What is brute force approach? Basically you have n features, you select every combination, every possible combination of them. Right? So a feature can either be there or no, right, in your set. So there are 2 to the power n possible combinations. So you check all combinations, whichever gives you the best. That's one thing we did for one project last time, the eating action recognition project. We published a paper on that, but the paper was published, but the technique was brute force. So that was not really attractive. Right? So we had to do 2 to the power n, and n was 17. So guess how many? So then that is brute force approach. Then there are embedded approaches, which means feature selection occurs naturally as part of data mining algorithm. Can you give me an example? Everybody is talking about it.
CNN.
What? CNN. Yes. So you have data mining algorithm which looks for patterns. It also selects features. Right? Deep learning. Then filter approaches. So which means that you filter out certain properties before you run the data mining algorithm. We don't need to discuss that, just like hand selecting features. And wrapper approaches, which means use the data mining algorithm as a black box to find attribute subset, which means that you don't have any idea of what features are important. You give it all of the features, you give to the data mining algorithm. Then you remove one. See what is the change in accuracy of the data mining algorithm, or what is the change in performance, right? And then, or what is the output? It might not change accuracy, it might not change performance, it just might change output, and you don't like it. Right? So then you add that and remove some other. So you use the data mining algorithm as a black box, look at the output and change the feature subset. That's how you can do feature subset selection. That's the wrapper approach. And the other thing that you can do is you can create new features from the existing features that are already there. So there are many different approaches. For example, Fourier transform, wavelet transform. I'm assuming everybody is familiar with it. If not, be familiar. As you need for assignment 3, Fourier transform, wavelet transform. And you need to understand what to look for in Fourier transform, right? Or wavelet transform. So these are simple processing concepts we are not going to discuss. One thing we can discuss, let's say frequency, Fourier transform plot, just to give you an idea of what you need to understand. So there is this example of 2 sine waves, and you do Fourier transform of it, you see 2 peaks. Why? where each frequency has a peak in the Fourier transform. Now, why do you see that it is infinite? Why do you see that the FFT here, this is the actual output from MATLAB. Why do you see that the Fourier transform is infinite? It has only two frequencies. Why does it have all those? There's no noise. You see, it's perfect sine wave. What is the basic assumption in Fourier transform? What signals do you do Fourier transform of? What? Periodic. It has to be periodic. The signal has to be periodic to have a unique frequency. Is this a periodic signal? Yes or no? Are you sure? It's not a periodic signal. Why? Because it's cut off. See, from 0 to 0.8 it's cut off. It's like a step. Then it goes sine and it falls. So now you know that step has infinite frequencies. If you do Fourier transform of a step function, it has infinite frequencies. That's why you can never see a Fourier transform that has just two peaks. You can never see that. Why? Because none of the signals are infinite. All the signals are chopped off. So you do not have periodicity there. Periodicity means it continues forever. You see same thing again and again, but it continues forever. So if you chop off, you'll never see Fourier transform which just has two peaks and drop. Right? So that's why you see all those. So this you have to be very careful about how you analyze Fourier transform, how you analyze wavelet transform. You have to know. This you don't really need to understand. Okay. Attribute transformation. Let's understand attribute transformation and what happens. We'll see some example of transformations. So simple functions like x to the power k, log x, e to the power x, mod box x, mod x. You know all these. We are not going to go through. Then there are standardization, normalization. These are very important. And these are very basic steps that you take. But this can make the difference between accuracy being 70% to accuracy being 90%. How? Because each sensor, so we are going to use very many different types of sensors in this research. So each sensor has a different level, different range. Right? You use one sensor one day on one person, then you use that same sensor on another day on another person, will show totally different levels. So if you don't standardize, if you don't normalize, then your algorithms will fail. So standardization, normalization, very simple things, but they help a lot. So what is standardization, normalization? You take a signal minus its mean and then do some transformation to make it lie between 0 and 1. So those are simple things, but still these are important. Then we come to the notion of similarity and dissimilarity. So we have to define metrics. Right? Similarity metric, dissimilarity metric. So if you are more similar, then that means that metric should go to 1, maximum value. If you are less similar, then the metric should have close to 0 or even minus. Right? Dissimilarity is just the opposite. If you are more dissimilar, the metric should have higher values. If you are less dissimilar, the metric should have lower values. So we define a lot of similarity, dissimilarity metrics, and we will see some examples. So one example is maybe, so these are some examples on attribute types and similarity, similarity metrics. There can be many. So nominal means just name, right? So one of the dissimilarity metric can be if the names are same. If the names are same, then metric is 0, right? There is no dissimilarity, so everything is similar. And if the names are not same, then the dissimilarity metric is 1, that is higher dissimilarity, right? So same similarity means you just switch it, 1 then 0. Now often for other types of attributes you cannot just switch it. So for example, Ordinal, the dissimilarity matrix is P minus Q divided by n minus 1. That's almost like a averaging value, average distance. And similarity is 1 minus that value. Right? Similarly, interval or ratio, the dissimilarity metric can be mod P minus Q, and similarity can be many other things like minus D or 1 by 1 plus D, and so on. Many different dissimilarity metric can be. Then distances are very important to define similarities and dissimilarities. Right? So there is a whole branch of research on mathematics on just distances, and Euclidean distance, Manhattan distance, and whatever you can think of. Maybe sometime you will come up with your own distance. Okay. So the P and K, these are k-dimensional or n-dimensional systems, n-dimensional data points, and that's how we calculate Euclidean distance. So this the book goes into calculation of distance. We don't need to. So Minkowski distance is what is a general form of the norm, right? L1 norm, L2 norm, general form. So general form of the distance is what? You just do pk minus qk to the power r, sum them up, and then take the rth root. Right? So that is Minkowski distance. Now, depending upon the value of r, you can have different distances. You can have if r equals 1, then you have Manhattan distance. R equals 2, Euclidean. R equals infinity, you have supremum distance. Right? So you have to calculate limit. A limit when r goes to infinity. So this is an example of Minkowski distance with L infinity, L1, L2. We're not going through this. You can just look at the book. So there, once you define a distance, yes.
Is R like the number of dimensions you want to?
No. R is not a dimension. R is not dimension.
Subset of?
No, it's not subset of it. It's your choice. R is your choice. N is the dimension. And so if we go back to Minkowski distance, that's okay. I think this confusion is there in the slide. I just didn't here. But don't confuse R with N. So don't. So Minkowski distance, this is the formulation. So where is N? N is in the summation. Right? So you can have R equals 2, R equals 1, 3, 4, 5, but same N. Does not matter. So if you have R equals 1, that's one type of distance. If you have R, that is the Manhattan distance. It can be in 1 dimension, can be in 2 dimension, 3 dimension, 4, 5, 6, whatever dimension. Right? That is N. N can vary independently of R. So R is just the power and the root that you take. So R defines what type of distance. N defines the dimension. So these are two different things. So when R equals 1, it's Manhattan. When R equals 2, Euclidean, 3, and so on. Okay. So distance, when you define distance, it has to have certain properties. Right? You cannot say anything is distance. Distance is a mathematical function and it has to have certain properties. So some properties is that the distance between P and Q that distant function has to be positive definite. This term positive definite is very important. We will use it later. So you have to understand what we mean by positive definiteness. Positive definiteness applies to a function. A function is positive definite if for its throughout its domain the function is greater than equal to 0. Right? Greater than equal to 0. So that's why it is positive definite. That is called positive definite. And it is 0 only if P and is equal to Q. Right? If you have two equal things, then only distance PQ is 0. Right? So dPQ is greater than or equal to 0 for all P and Q, and D of P comma Q is equal to 0. Right? Only if P is equal to Q. Right? So that is positive definiteness. And then you have to have symmetry. Symmetry means the distance of P comma Q is same as distance of Q comma P. Right? It doesn't matter what order you measure the distance. And then you have to have the triangle inequality that we all know that the distance of P comma R is less than distance of P comma Q plus distance of Q comma R. And that we have to have. So this dP comma Q is known as the distance. It is also same as the dissimilarity. Right? It's one of the ways to define dissimilarity. So a distance that satisfies this 1, 2, 3, these properties, they are called metrics. Right? So if I say that, okay, what is your metric? So metric you have to define in such a way that it follows the positive definiteness, symmetry, and triangle inequality property. It has to follow. So don't use the term metric in a loose way. What is your accuracy metric? A lot often people say, right? So if I say that what is an accuracy metric, then it has to be a metric that has three properties: positive definiteness, triangle inequality, and symmetry. Right? Otherwise, it's not a metric. Okay, similarities also have some properties, but those are not as extensive. So similarity, typically the maximum value is 1 when P is equal to Q. Right? And it has to be symmetry. So then the book goes into many different examples, right? Examples of similarity. So for example, if your objects are only have binary attributes, which means all attributes can either be 0 or 1, right? They cannot achieve any other real values. So if it has binary attributes, then you can define two coefficients: simple matching and Jacob coefficients. So these are just some definitions and some equations which we will use for exams, but we will not really need later. Right? But it's good questions for exams. Test you whether you remember. So similarity matching coefficient, SMC, is number of matchings divided by number of attributes. Which means if it is 0 and 1, the binary values, attributes are 0 and 1, then that means two attributes will either match or no. Right? Either they are both 0 or 1, both 0 or 1, or they are 1s and 0s. Right? So that's why this is called matching. So matching is this number of matches divided by the total number of attributes. So if you have two attributes, right? So two-dimensional system, then it can have all these values that P was 0 and Q was 1 and so on, right? So P is one data point, Q is another data point. So it says that M01 is the number of attributes where P was 0 and Q was 1. So you check the same attributes. So let's say it's an n-dimensional system. You check dimension 1 and count, okay, does P have 0 in this attribute and does Q have 1 in this attribute? Then you add 1 to M01. So like this you go over all the n dimensions, like counting how many mismatches, how many matches, how many mismatches are 0, 1, how many mismatches are 1, 0, how many matches are 0, 0, how many matches are 1, 1. You find out those, then you get these numbers. And then once you get those numbers, then those metrics are very easy to compute. So similarity matching is number of matches divided by number of attributes, and J, or Jacob coefficients, is number of 1, 1 matches divided by number of not both 0 attribute values. Not both 0 attribute values, very weird. So M11 divided by M01 plus M10 plus M11. Why? Because it's giving priorities. It's giving priorities to or it is actually removing data points which have no information, so 0. Actually, I won't say that. I won't say that they have no information, because they have the information that they are 0. Right? So they are just 0. The 0 is not given that importance. And then it goes on giving examples. So we will skip the examples. Cosine similarity. cosine similarity is another metric that is good to compare high dimensional vectors. Right? So an example is, okay, basically what is cosine similarity? You have two vectors, right? How do you determine cosine similarity? Basically dot product and divide by the magnitudes. So which means it gives a cosine of the angle between the two lines. Now why is this important? Consider gesture recognition problem. So gesture recognition problem means somebody did this, right? You want to identify this action for that person, right? And then the next time, instead of doing this, the person did this. Right? So the difference is somebody doing this and somebody doing just this. Same actions. But if you look at the accelerometer profile, you'll get one this big value and the other very small value. Right? How do you compare the two? Essentially, they're the same thing. So if you look at the time, so let's say every data point has a time axis and xyz, 3 axes, right? 3 plus 1, 4 axes. Time versus xyz. So if you look at that, then that will be a vector in 4 dimensions. Right? The entire action can be represented as one vector in 4 dimensions. If you consider 3 dimensions, then it won't be a vector. It will be a path. Right? But if you consider 4 dimensions, then it will be a vector. So time is also a dimension there. So if it is a vector, then how do you compare this action versus this action? If you compare with the magnitudes are going to be different. So you figure out that, okay, these two actions are different. But if you do take the angle between the vectors, you will see that these two vectors are the same angle, or very low angle. So that's why cosine similarity helps you when the magnitude doesn't matter. The magnitude of action doesn't matter, only the action matters. Okay? So it gives a little bit of a higher level similarity metric, or dissimilarity metric. Now there is another metric called extended Jaccard coefficient. So what you do is you take, so Jaccard coefficient was defined for only binary attributes, right? But you can, the extended Jaccard coefficients are defined for real attributes as well. So how do you do that? P and Q are 2 data points, so these are vectors. So you do dot product and divide by mod P squared, or the L2 norm minus the dot product. Why? I have no idea. It's just a distance. Then correlation, a lot of you know correlation already. So correlation means you take 2 signals, you align them, multiply each data points, sum them, divide by the number of data points. That's correlation. So what you do here, this is all mathematical term that they are explaining. So covariance of xy divided by variance of x divided by variance of y. Okay? So Sxy is this, Sx is this, Sy is this, and then you compute covariance, or actually correlation. Okay? So that is how you compute correlation, and there is the relation of correlation with covariance. And it then gives an example. Okay, here comes a very interesting point. This is very relevant. Everybody should understand this. And this has far-reaching consequences if you don't understand it, right? How do you figure out correlation by seeing data? By just looking at them. How do you figure out correlation? So the first one, what would you say? Does the first one have high negative correlation? Yes. How about the second one? How about the 8th one? What? Are they? How will you figure out? One way is that, spread out the zoom in, right? The other way is what? You draw lines. right? Okay, forget about that data for a while. So many data points. Are they correlated? Can you say that there is a positive correlation, negative correlation? What if you look at this? Only that area. You can say. Right? Now let's say somebody told you, fit a line through this. Fit a line through this. And there is some sign variation. But on an average, can you tell me whether you have a correlation or not? On an average. And we know it's varying. We know it's changing. But on an average, can you tell me whether it has a positive or a negative correlation? What does it have? Why? How will you draw the line? So in order to draw the line, you need 2 points at least. Right? Which 2 points will you select? What? You have some maximum and so this one, you select this one and you select this one, right? Maximum, minimum, and you say that okay, there is a negative correlation. So if I told you, okay, no, I will tell you later. The thing I will tell you later. I will give the labels of the graph later, and it might lead to some controversy. Okay, so that is one way. She says negative correlation. Any other answers? Why would I choose that maximum? Why would I choose it? Who forces me to choose it? A better answer would have been I will take some intervals and I will take these values and take a median of them, right? I'll take these intervals, I'll take these values and take a median of them. I'll take these values and median of them, right? So I will get some, if I plot the medians, I'll get some trends that is much more and less varying than that, right? Maybe I'll get this, then I'll take these values, median becomes this, I'll take these values, median becomes this, I'll take these values, median becomes this, these values, median is this, values, median is this, and finally I take this median, I fit a line. I can do that as well, right? I can do that as well. So in the first case, I say that there is a negative correlation. Now nobody is telling me, nobody is stopping me from doing that. Okay, I choose this as the maximum point and this as the minimum point. Nobody is stopping me. So I say I have positive correlation. I use this two technique. Then I use this technique to say that no, it's no correlation. Right? Now if I tell you that this is what will you tell me? Global warming or not? Can you tell me? You cannot. You cannot tell me. It's a different way of looking at the data. You will be surprised that is what is happening. Right? That is what is happening and is being passed as science. I am not saying this. I can send you a YouTube link of a Nobel laureate who is saying this.
How does the temperature change with time?
What?
In the plot, the basic plot would be different, right? The global average temperature would keep on.
I am not going to go into that. I have to save myself. Okay, so that's how you look at data, right? Correlation is a very weird metric, and you have to be very aware of how to find correlation, how to look at the data, and what is a scientifically accurate way of discussing correlation. Because correlation is a linear thing, and nothing in this world is linear. Correlation is a linear correlation, you find a line. Nothing in this world is linear, but you still use correlation. So you have to be very, very careful when you are using correlation. So that is the message, right? So just don't believe anything. Then there are things that you can do, that you can combine different similarity and dissimilarity metrics using some weights. That's not that big of a deal, everybody knows it. So these are different metrics that you combine using weights. There is one concept that we need to understand, density, because when we are talking about clustering, we will talk about density-based clustering, so that we need to see. So density is what? There are many different definitions of density, but the overall definition is that how many data points are there per unit volume. Right? That is the definition of density. So if you say Euclidean density means number of points per unit volume, and this volume is a square. Probability density means the relative likelihood for a random variable to take a given value. That is the definition of probabilistic density. Graph-based density is what? You have a graph and the number of edges coming out of a node. And that can be this density. So different definitions of density, and different definitions will result in data looking in different ways. Right? So one of the main takeaway from this chapter is that there are many metrics, there are many different ways of looking at data. Now if you want to be scientifically accurate, don't fix your conclusion before analyzing the data. So analyze the data and then argue about conclusion. Right? So that is the message from this chapter. Other things are not that important, you already know this. So that is the end of chapter 2, let's go to chapter 3. Chapter 3 again doesn't have that detailed information, you don't really, yes? Some questions? Anybody has questions? Yes.
So on correlations, it's the correlation between data points or correlation between different features?
It can be both. Data points, features, it can be anything. Correlation between two attributes, you can say also.
But examples we use, like the scattered points, are those the
Features, those are features on XY. So exploring data, so this chapter that we are going to talk about, this chapter doesn't have that detailed of an information. I mean, it discusses a lot of topics, but in very briefly. So this is not that important of a chapter even for your exams. So this discusses summary statistics, frequency, mode. These are statistical terms that you ought to know. Right? But we'll just briefly go over them. Then it also talks about visualization and all that. And it's a very small subsection of the chapter. So we won't be discussing in that great detail here. Right? So chapter 3 is we can kind of skip it, but let's just discuss the different things that are there. So summary statistics, mean, standard deviation, I'm assuming everybody knows. Frequency and mode. Mode, what is mode? Yes? Maximally occurring data point. And frequency is what? How many times a particular data point has occurred. Then percentiles, oh, there is some formatting problem. So you know percentiles. So percentiles means given an ordinal or continuous attribute x and a number p between 0 and 100. The pth percentile is a value xp of x such that p% of the observations of x are less than xp. It's got to do with probability density. This is how you calculate mean, median, and all that. It's not really. This information I'm thinking that you already have as background. So we are not going in detail of these things. Variance also, I'm not talking about this. There are many ways, many different ways of calculating variance. Then we go to visualization. There are many different techniques. One of the primary challenges of visualization is as data dimensionality increases, how do you see? How do you gather important information and see? One very important concept in visualization, I don't know whether it's discussed in any course or not, manifolds. Anybody has any idea of manifolds? Do you know what are manifolds?
Curvy data, which can be seen in one dimension. Like, you can consider a cube.
What?
Cube type of
Cube.
tube or S-fold, something like that. When
Oh, you are giving me examples. These are good examples. But what is manifold in general? So manifold, yes.
It's a space that is existing in a higher dimension, but you can actually represent it all as lower dimension.
Yes, exactly. So it's a space that is existing in higher dimension, and this space has to be continuous. So you cannot have holes in it, right? So this space has to be continuous, and it is existing in some higher dimension, but you can transform it and reduce its dimension without losing any of its features. And so that is a manifold. So an example of manifold is human brain. It's in 3D, right? Human brain is in 3D. But in our CIDAC, there is a professor, I'm forgetting his name. Sorry, I forgot his name. But he does excellent work on what? Anybody? I'm in trouble actually. Okay, so no, he does excellent work in manifold manifold representations and dimensional reduction from 3 to 2 of human face. No, brain, sorry, brain. Right? So now it defines distances in the manifold dimension, which under this transformation maintains their relative values. So for example, if you take the human face has nose, right? It's coming out. But how do you bring it to a page, two dimension? So you have to define distances that are that follow this contour. So when you do a transformation, this contour distance is maintained. It doesn't change. Right? So that is data visualization. That is one of the techniques that you can use to visualize as well as reduce dimension and use data mining algorithms on them. Right? So that is one of the techniques. But data visualization as a whole is a lot. It's a big thing, which is not really, we won't really discuss this in data mining. Representation, we don't need to see. So, what else is there? These are everything you know, histogram, box plots, all these things that you know. So I'm not going through this. Scatter plots, I'm assuming that you all know these things. So that is what we will talk about in chapter 3. So let's move on, right? Because we have other important things to discuss. Okay, let's talk about classification. So this is chapter 4. So we'll talk about classification. So let's recap because we have already talked about this earlier. Classification, there is a training set and there is a testing set, right? So training set, when you have a data matrix, there are a lot of attributes. One of the attributes is the class name, right? So in supervised classification, what you do is all the class name attributes are known. For a training set, you will learn some model, right? What models, we'll talk about that later. You learn some model, and then after you learn the model, you have an unknown data which means a data for which the attribute, the class attribute is not known, right? So you want to predict that class attribute. So basically, you represent the class attribute as a function of the other attributes. That's what is classification. So if you are given this training set, so you have a learning algorithm. You learn a model. What is a model? We'll come to that. This learned model, you apply that learned model and you find out test, the class of the test data. So training is often known as induction and testing is often known as deduction. Right? So these are some examples of classification. You already know some examples. Image classification. You give an image and it classifies it as car and all that. So there are many things, many different classification techniques. We'll talk about all of them. So there are decision tree based methods, rule based methods, memory based reasonings, neural networks, naive Bayes, support vector machines. We won't just stop there, but we'll talk about deep learning. We'll talk about reinforcement learning. And we'll finally end with, we might talk about Q learning, but I'm not sure, based on whatever time we have. I want to discuss collaborative filtering with you also, because that is one of the data mining tasks that recommender system uses, and that is very important for you to know. So collaborative filtering, deep learning, reinforcement learning, and finally we'll end with DeepMind. We'll have a discussion, we'll read the paper. We'll read the seminal paper written by Google. So let's talk about decision trees. Let's start the discussion on decision trees. So basically, what is the aim? The aim is you want to represent the cheat, that class level, in the form of some tree. So you want to come to that in the form of a tree. So the moment you want to generate a tree, the first thing you need is a root node, right? So how do you select a root node? Just select. Just choose. Now there might be matrix. There can be matrix defined to choose a particular root node, but for now let's just choose. Right? So we chose refund somehow. Now there are two options. Yes refund, no refund, right? So then this refund will have two child nodes. So if it is yes, then you take all the data points that are yes on refund and put it on one side, right? So what data points are on one side? Yes, data point is number 1, 4, 7. Yeah, 1, 4, and 7. These are on the yes side, and on the no side, the rest is on the no side. Now you go one side by one, go one by one, and analyze the children one by one. So you first look at the yes child, right? So you first look at the yes child and say, okay, do I have, also, what is the class level of all the child nodes that are yes? Okay. So I see that, okay, 1, 4, 7, so 1 has class level no, 4 has class level no, 7 has class level no. So everything is no. So my class level, everything is no. I do not have mixed class. I have a pure class, right? So that is the class level which has only one representative, right? In that class, the class which has only one representative class, that is called, or the set of points which has only one representative class, that is called a pure class. And if you have a pure class, you don't divide it further. You don't need to divide it further. Right? So you keep it like that. So that is now no. No means that is the class level no. Then you go to the no child. So no child, you say that, okay, 2, 3, 5, 6, 8, 9, 10 are no. So 2 is the cheat is no, 3 is no, 4 is no, 6 is no, 7 is no. No, 7 was not there. 8 is no, yes. 8 is yes. 9 is no, 10 is yes. So this is a mixture of yes and no. This is not a pure class. Right? So a pure node. It's called pure node. So this is not a pure node. So we have to continue. So if we have to continue, then that means we have to select another node. Assume another attribute that can serve as node. So what attribute do you select? You select one. Right? Somehow. So they selected marital status. Now marital status has 3 options: single, divorced, married. Right? It has 3 options. But somehow you decided, following certain metric, that married is a different story. Maybe they are less happier. Single, divorced is a different story. Maybe they're more happier, or vice versa. Yeah. It can be vice versa. So if we divide in that way, so if I want to keep it binary, so I said, okay, married. So how many inputs are married? So maybe 2 is married, yes, and the label is no. So 4 is married and the label is no. 5 is not the part. No, 4 is okay. 4 is not a part of this. 5 is a part of it. So 5 is divorced. So I don't care about it. 6 is married and no. 9 is married and no. Right? So all those are no. And I have a pure class because everybody that is not a cheat. Maybe then that's why it has a good effect. So all the classes are no. So I have a pure class, I don't go any further. Right? So I look at the single divorced class. I look at the single divorced class and I see that, okay, now I have to find a new node. Right? So select one. So let's select taxable income. That is the last node that is left. So taxable income, what I can say is that I can, so this is a real number, taxable income. It doesn't have options. It's a real number. But I have to convert it into some option. Because I have trees, right? I have to convert it into some option. So how do I do that? I use a threshold value. So I decided somehow, how will come later, somehow I decided that maybe 80K income is a threshold value. Right? So I say if taxable income greater than 80K, are you achieve? Or less than 80K, are you achieve? So let's look at it. So greater than 80K means 1 is greater than, yes, 1. Then 2, oh no, 2 is married, so 2 is not there. 3 is no, so don't care about 3. 5. 5 is greater than 80k. Okay, so 5. Oh, 5 is greater than 80k. We don't care. We care less only. Okay, somehow. Okay, figure it out. Right? So taxable income less than 80k. If it turns out that all are not cheap, and taxable income greater than 80k turns out that yes, you are cheap. Right? So using this training data, since we are given the labels, using this training data, we can build this tree. Right? We can build this tree. Now, once you have built the tree, what do you do next? So that's the induction process. That's how you induce a tree. So once you have induced a tree, then what do? You have to have a test data. Now before we go to the test, now let's go to the test data. So you have a test data. So test data is refund, no, marital status, married, and taxable income is just 80k. Right? Can you figure out whether this person is cheat or not? What you do is you look at the root node. Root node says that okay, you evaluate the refund status first. So refund can be yes or no. I see that refund is no. And so then you go to the next attribute, marital status. Marital status, single, divorced, married. I see that marital status is married. Immediately I say that it is not a cheat. That's how it tests the model. Now let's come back to the previous question. The previous question was, okay, there can be multiple models. Depends on how I choose the root node, how I choose the subsequent child nodes. Right? There are multiple models. So how I do that, how I do the induction step, that is the whole chapter. Decision trees. That is what is there to decision tree. How do I choose nodes? Right? The basic decision tree is very simple. If you know how to choose nodes, then decision tree is very simple. But how to choose nodes, that question makes it complex. So there are 3 types of nodes in a decision tree. A root node which has no incoming edges and 0 or more outgoing edges. An internal node which has exactly 1 incoming edge. You have to exactly 1 incoming edge. Why? We'll talk about that later. So exactly 1 incoming edge and 2 or more outgoing edge. And then leave for terminal nodes which has exactly 1 incoming edge and no outgoing edge. Okay. So these are the 3 types of nodes. Now tell me, why don't you have multiple incoming edges to internal nodes? Or even to leaf nodes? What's the reason?
It's like a top-down approach. So if in one node, if there are 2 incoming nodes, we don't know if that satisfies the other condition or not.
Why do we have to know? It's not really ambiguity, because you follow different paths, you go to the same one. What's the big deal? It's not ambiguous.
In every step we are making a decision.
Huh?
In every step we are making a decision.
Decision to eliminate some data points.
Because you're using pure nodes, that's why we need to have at most 1.
Kind of, yes.
Otherwise, we use probability.
Yeah, kind of, yes. So note this, that whenever you are following a node, right, you are eliminating some data points. Right? So if you have one root node and you go 2 different paths, then these 2 different paths means you have 2 mutually exclusive set of nodes. Right? Now if you come back, if these 2 paths come back to the same node, then what happens? You have 2 mutually exclusive set of nodes and you are trying to combine it or what? Not only redundant, it will be infeasible. The node, reaching that node will be infeasible. Right? So that tree won't make any sense. Because if you follow 2 different paths, the first point at which you follow 2 different paths, you divide the test data or training data into two mutually exclusive sets. Coming back to the same node means you are trying to combine it. And you know that combining it will lead to greater impurity because these were two different sets with two different classes. Right? So that's why you don't have edges, two edges coming on to the same node, incoming edges to the same node. Right? So those are the three different types of nodes that you have in decision trees. So there are many algorithms for decision tree induction. We will talk about Hunt's algorithm. We will talk about card and all those things. Those are I think in the book very briefly, but we will talk about Hunt's algorithm. So let's look at this Hunt's algorithm for decision trees. So let dt be the set of training records that reach a node t. So dt is the number of training records, or is the entire training record that reaches a node t. Which means we already said earlier that, right, that if you follow a path, then that means you are dividing the nodes, set of nodes, into two different sets. So if you come to a particular node, you come to it with a set of data points. Right? So that is dt. If dt contains records that belongs to the same class yt, then t is a leaf node labeled as yt. So it is the same argument that we followed for the initial example. Right? So if it is a pure class, which means it has all the training data points have yt as their class. And if that is the case, then stop there, you label that node yt. If dt is an empty set, then t is a leaf node labeled by the default class yd. dt can be empty, right? And if dt contains records that belong to more than one class, use an attribute test to split the data into smaller subsets. So now you have to do attribute test, and that is the most difficult part. What attribute we choose next? Right? So you have to choose one attribute that divides. One of the metric can be highest impurity. Now how do you define impurity? Right? So the attribute that leads to highest purity. Right? So you choose, you go through all the attributes and you define a purity metric and you find out the purity of the split. And then you choose the split that gives you the lowest impurity or highest purity and you keep that split. So that's how you can do it, but exact details, let's see. So Hunt's algorithm is very basic and that is what we talked about. Right? So we don't have to go over that example again. It's the same example that we said. So now the question is, how do we split? So Hunt's algorithm is a greedy algorithm, right? So it determines the best possible split right then and there. And that, with that data point, what is the best possible split? It takes it. So it's a greedy approach. But the problem is, even if it is greedy approach, how do we split the records? So which means, how do we specify the attribute test condition and which attribute to choose? Right? How do we determine the best split? Not only that, how do we determine when to stop splitting? Now just to go ahead, or just to give you a look ahead of the problem, of this question, determine when to stop splitting. If you cannot determine when to stop splitting, let's say the data set is such that you are never having a pure class. Right? It's a very complex data set, you are not having pure class. Worst case, what can happen? When will you stop?
We can allow some kind of error.
What?
We can allow some kind of error.
What error?
In a cluster like decision if there are 10% of non-class members.
No, I'm saying it's a data set that is very complex and you are never having pure classes. So you keep on splitting. What is the worst case that you can have? It's not an error.
Each record will be the leaf node.
Exactly. That is the worst case. That each record is the leaf node. Now if you have a decision tree where each record is the leaf node, can you use anything to test it? What will be the test accuracy? unless it is the same record as training. If it is different record, then it will wrong classification. So test accuracy will be 0. What is happening here? Overfitting. Right? So we will talk about overfitting, underfitting, in general, generalization error. We will talk about that a little bit later. So you have to determine when to stop splitting. Right? You should not let the tree run forever. If you let the tree run forever, in worst case you will end up with one leaf node per data point. So that is not optimal. So you have to determine a time when you need, or a condition when you stop splitting. So now let's answer the question how to specify test condition. There are many ways. It depends upon attribute types. Yes. So you have some nominal attributes, ordinal, continuous. So it depends upon how you split. So attributes, nominal attributes you can split 2 ways, or 3 ways, or multi ways, whatever. Right? So let's say multi-way split. There is a nominal attribute. So car type, family car, sports car, luxury car. You have 3 ways of split. So that's multi-way split. But you can also do binary split, which means you can combine. And you can say sports or luxury on one side and family on the other side. And you can do a binary split. Now, okay. So there's one important thing, that the size. You cannot do this multi-way splitting. You cannot do this, and some multi-way splitting you cannot do with ordinal data, right? So ordinal data, the split should be such that it keeps the order. So for example, that split, the size, small, large, and medium, that split may not be feasible. Why? Because you are negating the order. You are grouping small and large, but you are ignoring medium and keeping it in different class. So that might be a wrong way of splitting. But who says? Maybe I want that split. And maybe my metric is such that I need that split. And maybe I'm analyzing or mining data for small family cars. And so the families might buy SUVs, they might buy sedans, right? But they may not buy trucks, big trucks. Or they might not buy small 2-seaters. And so if I am doing that analysis, then this makes sense. Now, how do you split based on continuous attributes? So we saw that 80K, that taxable income, that was a continuous attribute. So you can do many ways. You can do discretization. You can say that, okay, take from 0 to 150 and have 50K increments. Right? So each 50K increment is one split. So you can have 30 increments. 3 increments. Right? So you can have 3 increments like that. Or you can just make a binary decision. There's the one that we did. Just have a threshold. Right? So we'll continue from here. We'll stop today.
Where they can select it and also make self-employed groups. Body. But if you don't have a group, so we'll publish sometimes. Yeah, set up this and self-employed.